Today I am going to explain my project title, Real-Time Cloud Infrastructure Monitoring and Log Analytics System. In simple terms, this project is about building a system that can handle and analyze a very large amount of data generated by computers in real time. Imagine companies like Google or AWS, they run thousands of servers and each server continuously generates data such as CPU usage, memory usage and disk activity. This data is called logs. In our project, we are dealing with around 6 lakh log records, which is a very large data set. The main challenge here is not just storing this data but processing it efficiently. So, our system should be able to follow this task. First, store efficiently. Second, search data quickly. For example, finding a log, usually its log ID. Third, perform analysis such as calculating average CPU usage over a time range. Fourth, update data dynamically when values change. To solve this, we use different data structures, mainly three base structures. For storing and searching, we use structures like AVL trees, red black trees, split trees, B trees, and bleep press trees. These structures helps in maintaining stored data and allow fast operations like insert, delete, and search, usually in logarithmic time. For analytic operations like range queries, we use segment trees and Fenwick trees. These are specially designed for handling range-based calculations efficiently, such as sum or average over a range. In our implementation, we first created a log in our implementation class to represent each record. Then we loaded data from a CSV file containing thousands of logs. We inserted this data into an AVL tree to maintain a balanced structure for fast searching. We also build a segment tree using CPU values to efficiently perform range queries. One important part of this project is to performance evaluation. We measure the time taken for operations like searching, insertion, and range queries using system time functions. We also tested the system under different conditions such as stored data, reserved data, and random data to observe how performance changes. We then stored the results and visualized them using graphs like dataset size versus execution time. This helps us clearly compare different data structures. We then stored the results and visualized them like using graphs like dataset size versus execution time. This helps us clearly compare different data structures. From our observation, we found that AVL trees provide balanced performance for searching and insertion, while segment trees are very efficient for range queries. B plus trees are generally preferred in databases because they support fast range scanning and are optimized for disk storage. In conclusion, this project demonstrates how choosing the right data structure is very important when working with large scale systems. It shows the difference between theoretical complexity and actual performance in real world scenarios. Thank you.